All right, good afternoon. So here we are for yet another lovely session of ENGR 2302 Engineering Dynamics. Today will be the first core lesson of the series, and this is the first sort of academic one. On the first lecture, we really just introduced the topic of engineering dynamics, and today we are getting into our first topics, which are the motion of particles. Okay. So let us begin. And I will always make sure we're still recording and we're good, so let's do that. Alright, so our topic for today is going to be the kinematics of particles. So we know that we defined dynamics last time, but dynamics has a few subcategories. Dynamics can include a few things. We did contrast between dynamics and kinematics, but if I want to provide some simpler definitions or more straightforward definitions or such, I might also like to distinguish between kinematics and kinetics. Kinematics. What is kinematics? Well, we discussed this last time. It is the study of geometry in motion, or the study of objects in motion, but really the study of geometry in motion. The study of geometry in motion, of the geometry of motion. The geometry of motion. And this means essentially that we're not considering forces or masses, etc. We are concerned only with the path of objects. So basically we're looking at displacement, we're looking at things like delta x, we're looking at v, we're looking at a, time, etc., without considering the cause of motion. The cause of motion. In other words, we're ignoring the actual forces and masses involved. And then kinetics is another way to break down, I made a contrast between kinematics and dynamics last time, but this is another way to break it down as well. If you want to consider both of these things within dynamics, kinetics is sort of the opposite. It is the study looking at the study of objects, the study of motion considering forces and masses. Considering forces and masses. And this is the material from chapter 11 of the Beer Vector Mechanics book. Forces and masses. I should say kinematics is more the topic of this. Really, these two topics are really we'll spend most of the entire course talking about. And so this is really, you can use this to predict what motion will result from forces. Results from forces, or what motion is needed to cause, or what forces are needed to cause motion. Predict what motion results from forces, or what forces are needed to cause motion. Result from motion. This can be an either-or relationship. So, for example, we might say a object is under the acceleration, under the force of gravity, and under the force of friction. What will its motion be? That would be going the first way. If I were to say a roller coaster goes through a loop of this radius, well, then and I asked you to find the normal force on it. That would be saying I am confining this thing to a certain path. What kind of forces will that body be subject to in order to have that path? Now, we're going to be talking about particle kinematics today. So we have kinematics, but I want to talk about a particular form of kinematics, and that is particle kinematics. Particle kinematics. And what is particle kinematics? Well, it is obviously the kinematics of particles. Of particles And so if I'm going to define this in terms of the kinematics of particles, well, then I better define exactly what I mean via a particle. A particle is an object of 0 dimensions. Of 0 dimensions. It has no size. Thus, all forces will pass directly through the center of mass. Pass through the center of mass. The center of mass. Thus, rotation is impossible. So, what I mean by this, if I consider an arbitrary non-point object, say like a rigid body, which we will explore later in the semester, a real object, even a 2D object here, will have some sort of center of mass. It'll have some sort of center of mass, center of gravity, etc. And if I apply a force to this, if I apply some force to this body, unless that force is directly lined up with the center of mass of this body will experience both rotational and translational tendencies. So it'll have a tendency to translate, which is referring to the motion of the center of mass, and it will also have a tendency to rotate, which means rotation about the center of mass. So we'll explore this later in the semester. Now in statics, we didn't allow the object to rotate. Instead, we said this thing is pinned down. What kind of forces do you need to prevent that motion? But as you imagine, if this thing was shrunk smaller and smaller and smaller and smaller till the point that all you had was an object of 0 dimension, well, it doesn't matter where I apply the force. There is only one choice on where it does matter where I apply the force, because I don't have a choice of where to apply the force. I can only apply the force directly on the particle. So therefore, this thing cannot experience any kind of any kind of rotation. It can only experience translation. So force and then tendency to rotate, or tendency to translate. So in red, I have the force. And in green here, I have tendency towards motion. And then tendency of motion. And then there are going to be a few types of kinematics of particles that we're going to consider. So there are two main types that we're going to be considering. And these are rectilinear and curvilinear motion. So I'm just going through a few introductory terms, and then we will see some actual numerical examples today. But as always, we start from the beginning. We always tend to start from more theoretical concepts and start with more grammar terms, just definitions, basic concepts, and then we move on to the more specific examples and such. So rectilinear motion. Rectilinear motion. Well, what does this mean? What do you think rectilinear motion means? Yes, an object moving in a straight line, yes. Does that mean it's moving at a constant velocity? Nope. It doesn't have to be at a constant velocity, no. So rectilinear motion is the motion of an object traveling in a straight line. Of an object traveling in a straight line. So this can mean a few things, but it will not actually have a constant velocity though. It's acceleration, velocity, position all change. All change. The only thing that is nailed down is that all of that motion has to happen along one axis. And so this type of, some examples of this would be things like, oh, a lot of the topics you'll see from even elementary, high school physics, like things like a ball is thrown up in the air and how long does it take to hit the ground? A car travels along a road in a straight line, and then we'll predict some things about it. This kind of problem. A train travels along a straight train track. All of these kinds of things. These are all rectilinear motion. Then we have curvilinear motion. So curvilinear motion is, well, if rectilinear motion is constrained along one axis, what do you think curvilinear motion is? 2D or 3D, yes. So fairly straightforward. You win the prize. Yes, you can predict simple things. Yay for simple patterns. Huh?
Leading question.
Yeah, it's kind of a leading question. So position, velocity, and acceleration of a particle, and acceleration of a particle as it moves along a curved line. As it moves on a curved line. On a curved line. All right, so we have that. So that makes sense. And it can be essentially, because of this, in order to be a curved line, it cannot be in one dimension. So we're either talking 2 or 3 dimensions. We're talking about motion in 2 or 3 dimensions. Okay, so moving along here. Let's talk more and specifically about rectilinear motion, because that's going to be our first topic to discuss. So our first major topic for today is rectilinear motion. So this one should be hopefully fairly straightforward, but we're definitely going to get into it a little bit more than you would with your standard high school physics class. We're using calculus. Okay. So, and you've seen some of this in even university physics, of course, but we're going to take things a bit further than you did there even. So, rectilinear motion. Rectilinear motion. Well, let's see. So we know it's a particle moving along a straight line, and we have many ways we can describe it. So, for example, the first thing we'll need is what we're going to call x, which is just going to be the position coordinate. The position coordinate, which we could really use any variable. We typically use x for rectilinear motion, is, of course, it is defined by a positive negative distance along an axis from a certain origin point. Positive or negative distance from some origin point on an axis from some origin point. From some origin point. So we'll need our position coordinate, which we'll use x. And so we have that. And that's fairly straightforward. And again, the motion of a particle, if I actually want to define motion of a particle, is really the change in its position to a certain value at some time t. Or I should say, the motion of a particle is only fully known at least, if we know its position coordinate for every time t. If we have a function that fully describes its motion, then we should be able to predict, we should be able to feed in a time value into that equation and exactly predict its location, if we know its position coordinate for every time t. And this is not necessarily a given. There are many systems that we may work with that we do not fully understand the motion. So for example, if I gave you if you think back to a simpler physics problem, like a simple energy problem, I might be looking at, say, one of those classic roller coaster problems where I have a roller coaster I release a roller coaster car at an elevation of 100 feet, it goes through a couple loops, and then at this other point that's at an elevation 50 feet, I ask you to find what's the velocity. That's a simple energy conservation problem. And I would be able to know, I could calculate the velocity at that point, even though I wouldn't know the full motion. I wouldn't know at time it reached that velocity. I wouldn't know how far it had traveled. But if all I cared about was the beginning state and the end state in terms of height and velocity, I could use an energy method to calculate that final velocity. Even though, so I would say I knew something about the motion, but I didn't really know its full motion. So to really describe the motion of an object, you're going to be able to create a graph describing the motion of that object. And it can be a fairly complex thing. It can be a fairly complex function. It can be anything you want, but I got to be able to describe its motion in terms of time t, either graphically, or I could define it through an equation, through something like x equals, I don't know, 3t to the fourth minus 6t or something. And no, this graph does not describe this equation. This is just a general arbitrary graph, and this is just a general arbitrary equation. If I had either this or this, I could say I truly understand the motion of a particle. If I don't have one of these, I can't really say I know the motion of a particle. If I have this one, I can find this one. If I have this one, I can find this one. But in order to really say I fully understand the motion of a particle, I need to know both its motion. Back up, I can't talk. If I am to say that I truly fully understand the motion of a particle, I need to be able to say that I can define its position at any location or at any time coordinate I choose to look at. All right, questions on what it means to know motion. Okay, hopefully fairly straightforward. All right. So now let us consider something where I want to look at the change in the position of a particle. So change in position of a particle. Or what if a particle's position is changing? Is changing. So what if a particle's position is changing? Well, let's take a look. So let's say we have a particle that's moving along an axis, and this is the x-axis, and here's my origin. So here's my origin, and let me say I have a few locations here. Maybe I have location, maybe I have this location P and a location P prime. So maybe this is the initial and this is the final. And the lengths here, originally this thing was at location X, but then after some time it's at delta X. And it was at P at time t, and it's here at time, so it was at here at time t, and it's at here at time t plus delta t. I know this can seem fairly simple, but I'm breaking motion down into its most fundamental mathematical principles here. And so here, this thing is going to have an average velocity. The average velocity of this particle is going to be expressed as follows. Average velocity. The average velocity is going to be equal to delta x over delta t. So this is our first fundamental basic equation for dynamics class. Very good to know. It just gets darker from here. It's all downhill from here. Maybe it's moving downhill. Maybe our axis is going downhill. No? Okay. Anyway, so yes, this is the simplest equation that you'll see in dynamics class, but they can't all be that easy, unfortunately. But in terms of calculating average velocity, it's not always too difficult. It is simply the change in x over the change in time or the change in position over the change in time, at least for rectilinear motion. Now, instantaneous velocity, however, is a little different. Instantaneous velocity is not measured over a period of time. It's measured as it's described at a singular instant. And instantaneous velocity mathematically is going to be defined as, I'm going to use the variable v, lowercase v, and it's going to be the limit as delta t approaches 0 of delta x over delta t. Delta x over delta t. And as we know from physics class, instantaneous velocity can be positive or negative. Can be positive or negative. And the magnitude or absolute value of this of instantaneous velocity is what? What is the magnitude of instantaneous velocity? Any takers? What do you think the magnitude or the magnitude of absolute velocity is, or instantaneous velocity? Instantaneous velocity. The magnitude of instantaneous velocity is referred to as, well, not the derivative. The derivative is how you would find the instantaneous velocity. Magnitude, what I mean by magnitude is speed. So speed cannot be positive or negative. So it's the particle's speed. All right? Okay. So let's think about this then. Now, again, so if I want to think about a object's velocity being positive or negative, well, if a particle is at somewhere along the x-axis here, and the particle is at point P, if its path is going to go to the right, assuming right is defined as positive, if it's moving to the right, its velocity will be greater than 0. If it's moving to the left, its velocity will be less than 0. Fairly straightforward. Then, if I want to look at the derivative relationship, and that's really what we're going to be using most of the time, from the derivative relationship, well, velocity again. If I want to, I can look at the limit, but really we don't really use limits all that often. Really, we use our derivatives. So it's limit as delta t approaches 0 of delta x over delta t, or it can perhaps better be thought of as dx over dt. Dx dt. In other words, if x of t, it's a simple example, and you've seen this many times in your physics and even in your calculus classes, etc. If x as a function of t is equal to 6t squared minus t to the third, then the velocity as a function of time will be equal to dx dt, which is equal to 12t minus 3t squared. Very simple, a very simple power rule, very simple polynomial rule derivative. Okay, so that's very simple. That's just the definition of velocity. So that's very simple, just the definition of velocity here. Okay. Sorry, having some issues. Okay. Having some technical difficulties here. Just 1 second. Okay, I guess I'll just use this for now. Okay. So this is really the definition of, comes back to the definition of velocity. Okay. Now, let's say I want to know something more about, maybe acceleration. Okay, now I have control. Okay, so let's move on to the next topic, and that is acceleration. So, as we saw that velocity is the change in position, well, acceleration is the change in velocity. So, acceleration. So now we're going to look at, let's consider something a little different. Consider a particle. Consider a particle with velocity v at time t, velocity v at time t, at time t, and v prime at time t plus delta t. So what I mean by this is, let us say that this thing is moving along the x-axis. Let me show this. So here's the x-axis, and at some point I have a particle. Initially it's here, and maybe over here it's here. And in terms of time coordinates, maybe this is t here, and this is t plus delta t. This is t plus delta t. And then, in terms of velocities, let's say that this is v at this point, at time t. So I'll have v here. And then this here is a higher velocity, or could just as well be a lower velocity, of v plus delta v. All right, so v and delta v. Or I could consider that v prime. So v prime and v, or just equal to v plus delta v. And it would be at coordinates. Here it would be p, and here it would be p prime if I wish to use that. And so the instantaneous acceleration would be simply, well, a is equal to the limit as delta t approaches 0, limit as delta t approaches 0 of delta v over delta t. Delta v over delta t. So, some things to consider, some notes on velocity. So a few notes on acceleration. Notes on acceleration. Well, let's consider a few details. Well, acceleration can be positive or negative. Can be positive or negative. We know this. But this is something that always has a tendency to bedevil certain students, especially when you start getting into negative velocities with positive accelerations or negative accelerations. So, if it's positive, a positive acceleration can really represent two things. a positive acceleration can represent a increasing positive velocity or a decreasing negative, yes, an increasing positive velocity or a decreasing negative velocity. Exactly, because the positive and negative is just the direction that it's going. A negative acceleration can represent a decreasing positive velocity or an increasing negative velocity. Or an increasing negative velocity. And then, if I look at the derivative relationships, well, I can say again that A is equal to the limit as delta t approaches 0 of delta V over delta t. It then is equal to dV dt, or simply d squared x over dt squared. Or just it is simply the derivative of the velocity with respect to time, or the second derivative of the position function. So, but this is all kid stuff. You've seen this stuff a million times by now. Hopefully not too bad. So if I were to run through a very quick example, fairly straightforward. If if V equaled 12t minus 3t squared, A would be the derivative of that. A would be dV dt, or it would simply be equal to 12 minus 6t. Again, fairly common, fairly easy, fairly straightforward. Okay, so let's continue on. Any questions about those basic derivative concepts? Fairly straightforward, I hope. Really nothing new. You've seen this a million times. You saw this in Calculus 1. Did you see this in Calculus 1? Maybe Calculus 2, probably Calculus 1. They usually cover this kind of thing because it's sort of a great example of Calculus 1, 2, 3, etc. Okay. So, let's see, what else might we do here? So we're going to look some more of these. And of course, we can talk about the graphical relations of these. I would also like to mention the graphical relations of these. So graphical relations, at least via the derivative relations. Let's discuss the graphical relation among among position, velocity, and acceleration. So graphical relation, actually before I do that, I might even go into the, might create a little table for the, perhaps for the, how might I say, the full integral and derivative relationships. The full integral and derivative relationships. So let's look at the integral versus derivative relationships here. Maybe I don't necessarily want to go into this exactly. Okay. Okay, that's okay. Maybe I will go into the graphical relationships. Trying to decide exactly how I want to cover this. So if I look at the then graphical relationships, if I look at the graphical relationships among, let's say, and these are all going to be among x versus xvt, v versus time, let me say versus t, v versus t, and a versus t graph. Well, what are the relationships here? Well, so if I have a position versus time, an x versus time, the slope of that graph is the velocity, or the instantaneous velocity. The slope is the velocity versus time. If I have the v versus time, the slope of that is the instantaneous acceleration. Then, if I want to go the other way, if I have the a versus t graph, well, the area under this curve, area under curve, the area under the curve, it does not give me the velocity. What does it give me? The area under the acceleration versus time curve will not give me the velocity. It will give me the change in velocity between the endpoints of that integration. And the same way, if you have the v versus t, the v versus t graph, the area under the curve gives you the change in position. The area under gives the change in position. It does not give the actual position. You will need a boundary condition to be able to determine where the actual position or actual velocity lies, depending on where you're going. Okay, and let's see. There are a few other ways to relate position, acceleration, etc. Okay, so let's talk about ways to describe acceleration or to describe motion. So let's think about something as simple as the motion of a particle. It's actually, I've covered so far looking at acceleration and velocity versus time, but that's not the only way. Ways to describe motion. There are many ways to describe motion. So for example, there are three main classifications that we'll consider. There are three main classifications. I may have the acceleration as a function of time, acceleration as a function of time, versus time. So this would be essentially acceleration is a function of time, f of t. And then if I knew the acceleration as a function of time, as long as I knew its velocity at one point and its position at one point, I could find all of the rest of its characteristics, all the rest of the characteristics of its motion. I can also say maybe acceleration versus position. So I could say a is a function of x. So instead of saying that the acceleration is this value at this time, I could say that its acceleration is this value at this x value. And we'll have ways we can transform between these. And I could also say something like, it may also be useful to say something like acceleration versus velocity. It may even be useful to classify things in terms of acceleration versus velocity. So in this case, I might say acceleration is a function of velocity. So and often we'll use different variations of these depending on the type of system that we're describing. So we're going to be looking at kinematics right now, so we're not worried about the forces on particles yet. But think about something where, okay, so we know that acceleration is intimately linked to force. We know that, right? We know that force equals mass times acceleration. The net force on an object is going to be equal to, if we remember Newton's second law, the sum of forces on an object is equal to the, or I could say maybe the force net on an object equals the acceleration net times its mass. That's not true? This seems fair. The acceleration on an object is equal to, or the force on an object is equal to its acceleration times its mass, or its acceleration is equal to its force divided by its mass. And so force and acceleration are directly linked, and that linkage factor, that conversion factor between the two, is the mass of an object. And so if we have a function that is relating velocity to force, or position to force, especially position to force, we can think of certain, I can think of certain forces where it may be very useful to describe motion in these ways. Obviously, acceleration versus time is the easiest. That's the easiest to differentiate, to integrate. It's nice and simple. But there are some things where it's very useful to consider, say, a force relative to a displacement. For example, consider a spring. If you have a spring, you have a, remember Hooke's law, F equals kx? In that case, the force that an object is experiencing on a spring is directly related to its displacement. If you pull the spring back further from its 0 point, you'll experience a greater force. If you pull it less, you experience less force. So that's a case where acceleration versus position makes a lot of sense. Can anyone think of a case where acceleration versus velocity would make a lot of sense? Can anyone think of a system, in other words, where the force is directly related to the velocity of an object? Someone mentioned friction, but maybe not necessarily friction, but you're getting warmer. What about a type of, so when you say friction, I usually think of friction versus, say, the ground or something, but there's another type of, what about friction versus the air, or in other words, air resistance, drag, in particular drag. We'll see this later in the semester, but drag force is directly related to the velocity. The higher the velocity, the higher your drag force. And in fact, it's proportional to velocity squared, not even to linear velocity. So we can see that there. So in the case of describing drag, so for example, if I were describing the motion of an object through the air, and I was not ignoring air resistance like we do in say, elementary, high school physics, it would be very useful to describe the forces in terms of velocity. But anyway, so let me look at the derivative relationships and integration relationships for all of these things. Let me create a little table here. So this is going to be some nice, fun calculus for the first day of class, or second lecture, I suppose. We already had the light day on Tuesday. Okay, so let's look at the kinematic relationships and the derivative relationships here for each of these. So I'll create a little table here. And I'm going to use 3 rows here. And what I'll have if A is, let's say A is A of t, so A is a function of time. A equals here a function of x, function of position. And here A is a function of velocity. A equals A of v. Then the kinematic relationship, or the more derivative relationship, and the integral relationship. So here, well, the derivative of this is fairly simple. dv over dt is going to be equal to a as a function of t. dv dt is equal to a as a function of t. For here, dt, well, dt is equal to dx over dv, or sorry, dx over v, because we know that v is equal to dx over dt, so therefore dt is this, and we know that a is equal to dv dt, so therefore v dv dt, or v dv I should say, is equal to a of x dx, yes, a of x dx. And if I know that dv dt equals a of v, then v dv dt, or v dv dx, I should say, dv dx equals a of v, using this relationship here. Or sorry, there. Okay. And there you have that. And so then if I integrate these, if I want to look at the integral relationships, here, the integral from v naught to v dv is going to be the integral from 0 to t of a of t dt, and the integral from v naught to v of v dv, so I'm basically integrating both sides of these, will be the integral from x naught to x. So I just want to create this big table of integrals, and then we can use these later on. A of x dx. And then I can look, maybe break this down, maybe do a bit of integration for each of these. And the integral of v naught to v of dv, I should say, of a of v is equal to the integral from 0 to t of dt, or simply, or finally, the integral of x naught, the integral of dx, I should say, from x naught to x is equal to the integral of v naught to v, from v naught to v, of v dv of a of v, over a of v. And I know that's some wonderfully dense calculus, but we'll look at that a bit more later today. So let's see. All right, I think that'll do it for this portion of the lecture. I think y'all maybe would y'all like to take a break? Okay, so I think that might do it for this portion of the lecture. We will, I wanted to introduce these derivative and integration, I wanted to introduce these derivative and integral relationships, and then we can come back and look at some example problems after the break.